Hello, my name is Christian Hessler. I'm a graduate student from the University of Michigan Dearborn, and today I present a non-contact method for extracting heart rate and respiration rate from human subjects using thermal cameras. Heart rate and respiration rate are two fundamental vital signs used to diagnose a person's health and well-being. Our goal is to extract these two physiological signals from the thermal domain by monitoring physical characteristics such as breathing and blood flow by observing subtle changes in skin temperature. Our study is just one example of a much larger area of research known as biosignal analysis. Today you can see biosignal analysis being applied in a wide array of applications. The widespread use of smartwatches and fitness bands paired with health monitoring apps demonstrates a growing interest in collecting and tracking physiological data even in our day-to-day lives. First of all, we need to establish a reliable way to collect raw physiological data. Now, the traditional approach in the past has been to use what we call contact-based sensors. These are sensors that require direct contact with the subject's skin. While they are generally pretty accurate, there are several drawbacks to using these types of sensors. If we take a look at this ECG heart rate monitor, we can see that it requires several electrodes to be attached to specific locations on the subject's body. If the electrodes are not attached properly or placed in the correct locations, the sensor may fail to provide accurate data. Secondly, the adhesive material on the electrodes can tug on the skin, which may cause pain or discomfort for the subject. One major concern here is that any discomfort imposed by the sensor could potentially alter the subject's mental and physical state. For that reason, less invasive methods are ideal for collecting unbiased measurements. In contrast to contact-based sensors, thermal cameras provide a completely non-invasive method for collecting physiological data. In order to collect this data using thermal cameras, we need to understand how the body absorbs and releases heat in order to maintain a constant core body temperature, which is crucial to our survival. Our body regulates its temperature through a process called thermal regulation. Our skin plays a vital role in thermal regulation because our skin receives signals from control centers in the brain to maintain the body's core temperature. Thermal imaging utilizes this principle to detect thermal radiation emitted from the surface of the skin in response to various internal and external stimuli. As a matter of fact, the subject need not even be aware that a thermal camera is collecting their data. If we set privacy concerns aside, there is a very effective way to collect natural, unbiased data. For this reason, previous works have proposed the use of thermal cameras for real-time applications such as fever screening at airports to prevent the spread of sickness, which unfortunately has become a primary concern for everyone in the midst of the current coronavirus pandemic. In this time of social distancing, non-contact methods are becoming even more important to prevent the spread of the virus. Despite these benefits, there are a few drawbacks associated with the use of thermal cameras. First, they require a direct line of sight with the subject's face in order to extract accurate physiological signals. Cost is another hurdle preventing widespread adoption of thermal imaging. Thermal cameras are becoming less expensive, but high-quality cameras still cost several $1,000s. For our research, we used our own dataset consisting of multimodal recordings collected from 104 undergraduate and graduate students with a gender distribution of 53 females and 51 males. The subjects were between the ages of 20 to 45 years old and of various ethnicities. 7 sessions were recorded per subject. In 2 of these sessions, the subjects were instructed to sit still and breathe normally. In the remaining 5 sessions, the subjects were asked a series of questions to keep them engaged in conversation. Each session consists of a thermal video recording of the subject's face in addition to several contact-based sensor readings. Therefore, a total of 728 thermal videos with accompanying sensor readings were analyzed. In this study, we're only interested in analyzing the temperature of the face. So I begin by cropping the face from the background image to eliminate any other heat sources such as the subject's neck or hands. Once we've detected the face, we continue to narrow our search by focusing on particular regions of the face where we are likely to observe the greatest changes in skin temperature. Studies in the literature suggest that the most effective areas are the forehead and area around the eyes since they both contain a high concentration of blood vessels near the surface of the skin. Then we calculate the average temperature across a set of pixels within the region for every frame in the video to construct a raw thermal signal. From this point, The majority of our work focused on searching for the most effective signal processing methods to filter the thermal signal in order to isolate the heart and respiration signals. Finally, our hope is that future research will build upon some of the ideas presented here to utilize physiological signals extracted from the thermal domain in a variety of applications such as deception detection, emotion recognition, or stress detection. Perhaps someday in the future, we will be able to extract signals from the thermal domain which are just as accurate, if not more so, than those collected from contact-based sensors. We began our study by developing a method to extract respiration rates from thermal videos. First, we extracted the thermal signal from a region surrounding each subject's nose, known as the maxillary region. We normalized the signal to produce a new signal with a mean of 0 and standard deviation equal to 1, which simplifies further calculations and provides a better frame of reference. Next, we downsampled the signals to remove noise. In this case, noise may include subtle metabolic contributions or extraneous frequency information introduced by sensor air. We reduced the frequency from 100 Hz to 25 Hz to remove noise without distorting the breathing signal. After preprocessing and filtering, we applied a continuous wavelet transform to both the sensor and thermal signals to extract a cyclical waveform at a given frequency which resembles a breathing signal. Furthermore, we defined an algorithm to calculate the breathing rate from this resulting signal. The algorithm analyzes the signal to predict the number of inhaled breaths in the video, which we then use to calculate a rate measured in breaths per minute. Finally, we calculated the cross-correlation between breathing signals extracted from the thermal images and those measured by the abdominal chest strap sensor to measure their similarity in terms of a correlation coefficient. As we saw in the previous slide, the continuous wavelet transform was the final transformation we applied to the signals in our dataset to construct the thermal, breathing, and heart rate signals. Our decision to use the continuous wavelet transform was influenced by the fact that wavelets are particularly well suited for analyzing non-stationary signals. Biological signals are often non-stationary in nature due to the fact that they may actually be composed of multiple physiological signals that result from numerous chemical interactions that occur in the human body. The continuous wavelet transform analyzes the signal in both the time and frequency domains. It achieves this by using a scale and translation parameter to compare the original signal to compressed and stretched versions of the mother wavelet. For that reason, choosing appropriate mother wavelets is a critical step in constructing waveforms which resemble breathing and heart rate signals. Our selection of mother wavelets was primarily influenced by previous works in the literature which published positive results by using these particular wavelet functions to model breathing and heart rate signals. Our heart rate extraction method follows the same principles used by the respiration rate method. However, we performed some additional steps and modified some of the signal transformations to account for attributes specific to the heart rate signal. We developed our own method for estimating resting heart rates of subjects using thermal data collected from the inner corner of the eyes known as the periorbital region. This is a departure from previous works which often use the forehead or neck to extract heart rate measurements. First, we applied image binarization to segment areas within the region which exhibit thermal characteristics related to blood flow. For each video, we define a threshold based on the 25% hottest pixels in the image. This threshold is required to ignore residual heat from the blood vessels which gets diffused to the surrounding tissues. The following images demonstrate how OTSU's method tended to undersegment warmer patches of skin, while manual thresholding segmented only the warmest tissues surrounding the eyes. This is a critical step in our analysis because we're only interested in capturing skin temperature changes which are directly related to changes in blood flow. After constructing the raw thermal signal using the periorbital region, we followed the same procedure previously outlined for extracting the respiration rate. The only exception is that we use different mother wavelets to transform the final signals. In conclusion, thermal imaging provides several benefits over contact-based sensors. Recording thermal video is far more convenient compared to attaching multiple sensors to the body. Thermal cameras can potentially screen people in seconds compared to the time-consuming task of outfitting someone with an array of sensors. Modern technology is facilitating the development of real-time thermal imaging systems that are sensitive to subtle variations in skin temperature. So there is a lot of potential for the use of thermal imaging in medical applications as well as research in human behavior. In this study, we developed a solution which integrates image and signal processing techniques to extract various physiological signals from thermal images. Specifically, we have proposed different methods for capturing temporal features in the face and for filtering thermal signals. Our results show a significant correlation between respiration rates extracted from thermal imaging and those recorded by contact-based sensors. Mean respiration rates extracted from the thermal domain were within a range of 1 breath per minute from the mean sensor-based measurements. We're also able to establish an average correlation of 0.6 between thermal and sensor breathing signals. Finally, we extracted heart rates from the thermal domain as well. The mean difference between the sensor and thermal heart rates was 5 beats per minute with a 99% confidence interval. Our research has shown that non-contact approaches using thermal imaging represent a reliable alternative to using contact-based sensors. Thank you for listening, and I hope you enjoyed this presentation on extracting heart rate and respiration rates from thermal images.